So, just how important is the CDF W boson mass measurement? In a recent video, that new Fermilab result on the W boson mass, we discussed a recent result from the CDF experiment. They reported a new measurement of the mass of the W boson that deviates from the standard model prediction by 7 sigma. Here we're going to give a bit more background on this result. Since we're talking about a statistically significant deviation from the standard model prediction, here we'll cover 2 topics. First, we'll talk about where the standard model prediction comes from, and after that, we'll talk about the experimental context of the new CDF result. Here are the references for both the CDF result and the standard model prediction for the W boson mass. These, along with a few other references, can be found in the video description below. There are a few videos on this channel which might be useful for understanding what we're going to talk about here. First, if you want to know what the CDF Collaboration did to measure the mass of the W boson, you might want to check out the previous video, that new Fermilab result on the W boson mass. If you'd like more background on what 7 sigma and related terms mean, you can check out the Understanding 5 Sigma playlist. And finally, this result is interesting because signs of physics beyond the standard model could show up as tiny deviations from standard model predictions. So you might be interested in the video, The Standard Model is Probably a Spherical Cow. Okay, with that, let's talk about where the prediction for the W mass comes from in the standard model. So here's the particle content of the standard model. We're interested in the W boson, which, along with the photon and the Z, is one of the gauge bosons that mediates the electroweak interaction. We'll also have to talk at least a little bit about the Higgs boson. We will start by giving some approximate expressions which hold for the electroweak interaction in the standard model. One of these will be an approximate expression for the standard model value of MW. Now we have some physics students which watch this channel, so on the right-hand side of this slide I've put a bit of jargon. For those students, these approximate expressions, including the one for the W mass, are tree-level relations. For everyone else, just know that we'll be giving a spherical cow approximation for MW. After we give these approximate relations, we'll talk about why they're only approximate and why they need corrections. Okay, let's get started. In the standard model, forces are mediated by the gauge bosons, which are the photon, denoted here with the Greek letter gamma, the W plus and minus, the Z, and the gluons. The electroweak theory unifies the electromagnetic and weak interactions. So we'll be looking at how the photon, the Z, and the W interact with the other particles in the standard model. The electroweak theory lays out the form of the interactions between the photon, W, and Z, and the other particles in the standard model. It contains 3 parameters, G, G', and V. We'll briefly discuss each of these. We'll start with G. G controls the strength of the coupling of the W to the other particles in the standard model. Here we draw an interaction between a W and a pair of standard model fermions. The strength of this interaction is determined by G. For example, the top quark usually decays to a W and a B quark, we might want to calculate the decay width of the top quark, which is related to its lifetime. To do this, you need to know G. Okay, next let's look at G prime. It is also a coupling, but it is more complicated. If we look at how the Z interacts with a fermion, the strength and form of that interaction will depend on both G and G prime. We can also look at how the photon interacts with other particles in the Standard Model. Its interaction is determined by the charge of the particle, written here as QE, where E is the absolute value of the charge of the electron, and Q is a numerical factor, like 2/3 for the top quark. E is related to G and G prime. So measuring electric charge can give us some handle on G and G prime. Okay, now for V. This is the trickiest of the three, and we won't go into much detail. V is what is called the vacuum expectation value of the Higgs field. You might have heard that the Higgs field gives mass to the fundamental particles in the Standard Model. The couplings of the Higgs to other particles is directly related to their masses. Let's look at how the Higgs boson couples to a fermion, here labeled F. The Higgs couples to this fermion with a coupling that we'll call lambda F. Lambda F is unrelated, as far as we know, to G and G prime. The mass of this fermion is directly related to lambda F. The mass, mF, equals lambda F times V over the square root of 2. So, for example, the mass of the top quark is lambda T times V over the square root of 2. And similarly for the bottom quark. The interactions of the Higgs with the W and Z are not the same as the interactions of the Higgs with the fermions. But the masses are still related to couplings, and they are still proportional to V. In particular, the W mass is GV over 2. Now, unfortunately, we don't measure G, G prime, or V directly. But luckily, there are lots of experimental observables that we could measure to get insight into G, G prime, and V. Since we need the values of 3 parameters, in principle, we can extract them if we measure 3 observables. Since we want a very precise prediction for MW, it makes sense to pick the 3 best measured of these observables. These are Mz, the mass of the Z boson, G Fermi, also called the Fermi constant, and the fine structure constant, alpha. Let's start with the mass of the Z boson, Mz. The Z was precisely studied at LEP, which collided electrons and positrons at center of mass energies near Mz. Each of the 4 experiments, Aleph, Delphi, L3, and Opal, made a few million Z's. Precision studies of the Z line shape gave 91.1876 plus or minus 0.0021 GeV for the mass of the Z boson. Okay, next, the Fermi constant Gf. This is derived from the muon lifetime, which is inversely proportional to the square of Gf. Here is the primary Feynman diagram for muon decay. The muon disintegrates into a neutrino and a W. The W then disintegrates into an electron and an antineutrino. The intermediate presence of the W makes G Fermi inversely proportional to the W mass squared. It also picks up two factors of G, which controls the coupling of the W to fermions. So, up to a numerical factor, G Fermi goes as G squared over MW squared. A few slides back, we said that MW was GV over 2, so G Fermi is actually proportional to 1 over V squared. Here is its numerical value, known to better than 1 part in a million. Okay, next, let's look at the fine structure constant, alpha. Alpha is equal to the charge of the electron squared over 4 pi. So measuring alpha is equivalent to measuring electric charge, which we saw could be expressed in terms of G and G prime. Alpha can be extracted from measurements of the anomalous magnetic moment of the electron or from precise measurements involving rubidium or cesium atoms. It is known to better than 2 parts in 10 billion. So, we can take these 3 highly precisely measured values and from them extract MW. Here is the relation between the W mass and MZ, G Fermi, and alpha. Again, for the physics students, this is the tree-level expression. If we substitute the values for MZ, G Fermi, and alpha into our equation, we get that the W mass is about 80.9 GeV. I haven't bothered to put an error bar on here from the uncertainties of the input parameters because it would be negligibly small. This value of 80.9 GeV, though, is off by about 0.6 GeV. We can compare that to the precision of the CDF result, which is 9.4 MeV, or 0.0094 GeV. This discrepancy is not caused by the errors on MZ, G Fermi, or alpha. Clearly, something is not right. Okay, we said that we could get MW from these 3 parameters. Alas, if only it were that easy. In fact, what we have obtained is only an approximate value for MW in the Standard Model. Why is our result only an approximation? Again, it's not the error bars on MZ, G Fermi, and alpha. The problem is that the relations between MW and these quantities that we used were themselves only approximate. Let's go back to G Fermi, which is obtained from muon decay. We wrote down the primary Feynman diagram that contributes to this decay. But here's another one. Here, the W oscillates into a top-bottom quark pair before turning back into a W. This diagram gives a much smaller contribution than the simple diagram, but it does affect the experimental determination of G Fermi. We can also look at the fine structure constant. This is related to electric charge, which controls how the photon interacts with other particles. But more complicated diagrams also come into play. Effects like these cause the relation for MW, which we wrote down, to be not quite right. We need a very precise theoretical prediction of MW to compare to the very precise experimental result, which is known to about 1 part in 10,000. So corrections to this formula must be calculated. That is extremely complicated, and we won't cover the details here. Also, once we include these corrections, we also need more inputs. For example, we need to know the masses of particles which can enter into these loop diagrams. So, to get a very precise value for the standard model prediction of MW, 3 parameters are no longer enough. Additionally, these corrections to MW also come with their own uncertainties. So the idea is to extract the standard model parameters from a wide variety of experiments, not just 3. Therefore, the value of MW predicted by the standard model is extracted from a fit to many experimental results. And we also need precision calculations to compare with those experimental results. Here are some example measurements other than MZ, G Fermi, and alpha, which go into the fit. Neutrino scattering measurements, the mass of the Higgs boson, the lifetime of the tau lepton, the mass of the top quark, other observables from the Z-pole, etc. All that work yields a predicted value for the mass of the W boson, shown here. Its precision is very good, 6 MeV, a bit better than the experimental error bar quoted by CDF. This is the value which is compared to the experimental measurement of MW. This is important because it's possible that an early sign of new physics would be slight inconsistencies between measurements of different standard model observables. For more info, check out the video, "The Standard Model is Probably a Spherical Cow." Okay, with that, let's look at the context of the CDF result. So, the recent CDF result is the most precise measurement of MW ever made. If we compare CDF's measured value with the standard model prediction, we get a difference of 77 plus or minus 11 MeV, which is a 7 sigma discrepancy. 7 sigma is a big deal. For a more quantitative idea of what it means, check out the Understanding 5 Sigma playlist. The CDF measurement is not the only measurement of the W mass. There has been a long history of measurements of MW. UA1 and UA2, who discovered the W, measured its mass with error bars between about 1 and a few GeV. The LEP experiments measured it with error bars of about 50 to 70 MeV. D0, which, like CDF, ran at the Tevatron, also measured MW. And there are now results from LHC. Here we will only look at the experiments with the smallest uncertainties. Here is a plot of 4 measurements of MW compared with the standard model prediction, which is given by the yellow band. The CDF result is on the right. We can compare this with results from Atlas, D0, and LHCb. The CDF result is above the standard model prediction by 77 MeV and has a tiny error bar of 9 MeV. So, the most precise experimental result disagrees with the standard model prediction by 7 sigma. Note that it is the precision of the result that makes it potentially very important. There do exist previous measurements with similar values, but with much larger error bars. On the other hand, the 3 next most precise results are in agreement with the standard model prediction. They have error bars of about 20 to 30 MeV. This is definitely an uncomfortable situation. There isn't so much one can say now, except that sorting out the reason for the discrepancy between the experimental results is probably not going to be easy, and it's probably going to take a while. So the takeaway point is that the CDF result is very important if it's right.